So the last class of acids and bases, and this one is the broadest and perhaps the most important one, because when we look at organic chemical reactions, we will always think of them as Lewis acids and bases, or what we will soon call them electrophiles and nucleophiles. So a Lewis acid is defined slightly differently than a Bronsted-Lowry acid, and we simply call it here an electron pair acceptor. So it accepts an electron pair. So this electron pair is going to the Lewis acid. Now, in this case, not all acids, this is weird, especially sometimes students think about it, is that not all acids have protons. There are some, like, for example, BF3. If you were to draw BF3 from Gen Chem, in fact, students ask why, and Gen Chem doesn't have an octet, and what would it do? Again, it has an empty shell. And of course, more specifically, a p orbital has an empty p orbital. So it only has 6 valence electrons. So it can accept an electron pair. Of course, there are others where you have carbons, like the ones we did with the formal charges, is that they have also a positive charge. They also have an empty p orbital. Once again, they have 6 valence electrons. So they can receive a lone pair as well. And of course, we're going to see this a little bit later, but here you have a less electronegative atom bound in a polar bond. So if you have, for example, something like HCl, where H is delta positive and Cl is delta negative, it can accept a pair if you break this bond. Now, on the other hand, so again, we're going to call these soon electrophiles because they love electrons. They accept electrons. Phile from Greek means from um, philia, which means love, to love electrons. So these are what you want to end with is those are electron poor or deficient. Now, Lewis bases are the opposite. Those are electron pair donors. So they actually give away electron. And some of them are the following. So let me go to the next page here. So all Bronsted-Lowry bases are Lewis bases. Absolutely. So for example, we could not disagree with Bronsted-Lowry that this is also a Lewis base because it has plenty of electron density. So again, it can donate one of these lone pairs. In fact, water can work as well. Ammonia, or even amide ion. So these are electron uh, pair donors. They have plenty of electron density. You see it right there, right here. And of course, all of this right here. So the golden rule here is that electron-rich species react with electron poor. So the electron-rich, and you have the electron poor, it's always this way. From the electron-rich, and let's actually put the 2 dots here. You have a pair of electrons, they go this way. This is a very important part to remember. And we call this a nucleophile. So becomes soon that you will learn about this is that the Lewis base, here's the Lewis acid. Once again, the Lewis base donates to the Lewis acid or the nucleophile. We use this one, and the electrophile E. They react this way. So again, they go from electron-rich Lewis bases or nucleophiles to electrophiles, Lewis acids. Those are electron poor. Quickly, how do we do these reactions? So you have to use also curved arrows. So you go from, again, the curved arrows go from the Lewis base to the Lewis acid, of course, with a lone pair. So let's look at this example right here. Right away, you need to identify the one that has any pairs of any pair of electrons that can donate. Well, right away, it's very clear that we have a pair of electrons right here. So this must be our Lewis base. This must be our Lewis acid. So again, what is this going to do is that it's going to donate an electron pair And how is that going to happen? Well, the arrow always goes, remember, from the electron rich to the electron poor. There it is. Now, formal charges are your best friend. On 1, 2, 3, 4. N has now supposed to have 3 bonds. Anything above 4, this is going to be a positive. So yes, so this is positive. So if this is positive, then, and we started with neutral, then one of these must be negative. Well, the only one changes boron when you can calculate it using the method. So here's what we call our product. This is our product. Sometimes it's called an adduct, but we're not going to use that terminology. So let's look at the next one. And by the way, in this one, I want to say is that it accepts an electron pair. Once again, it has an open shell and empty shell. Same thing here. You have a lone pair. That's your Lewis base. This is your Lewis acid. And of course, we draw the same. Still have one more lone pair on it. But oxygen now has 3 bonds, so it must be a positive. What changed? Must be the Al, it's a negative. It's in the same group as B, by the way. Same thing here. Which one would be? You should pause and actually work on this one. So again, here's our Lewis base. Why? Because we have lone pairs. This one has a positive charge, so clearly it's a Lewis acid. It's going to accept the protons, the electron pair, I'm sorry. So we go here. And our charge is positive because we have oxygen with 3 bonds. Now, what happened to C? C has 4 bonds, so it should be neutral. Notice one quick thing about this is that if you start with neutral, you must end with neutral. And we do have neutral molecule because the positive cancels out the negative. Same thing here, positive cancels out the negative, it's neutral. Here we started with a positive on this side, positive. This is neutral, so it's positive overall. So you end up with positive. So again, when we come to class, we will learn about more involved examples, but please start practicing and again, look for patterns and do enough of these problems.